Good afternoon and welcome to this session. I'm Steve Tompkins, Head of Business Development for SFG20. I'd like to welcome Mark Grayson. He's going to be presenting to you today on embedded carbon in the Hvac lifecycle. Mark Grayson's Head of Product Development and Strategy Delivery for Mitsubishi Electric. During this session, you can obviously post questions and answers during the Q&A, and hopefully I will join you at the back end of that. So I'd like to hand over to Mark now, who will present the session.
Great, thank you, Steve, and good afternoon, everyone. And thank you very much for your time today to talk about this, what we feel is a really important topic. Improving the environmental impact of buildings is now a major priority given the climate crisis. Recently, there has been a drive to shift the generation of heat to electricity using heat pumps so that we can drastically cut the use of fossil fuels such as gas. This, along with improvements to the efficiency of a building's fabric, which reduce the overall heating load, and the increasing decarbonisation of the electricity grid have led to reductions in the operational carbon of buildings. However, the whole life carbon impacts of mechanical and electrical and plumbing products do not end with operational carbon. To make well-informed decisions that will help mitigate global warming, consulting engineers, architects and clients need to embrace whole life carbon emissions. This term refers to both operational and embodied carbon emissions from manufacturing, transportation and construction, repairing and maintaining a building, through to deconstructing the building and processing waste. This image is a graphical representation of the global average temperatures between 1850 on the left to 2018 on the right, created by Professor Ed Hawking at the University of Reading. Throughout the past few weeks, this graphic has been used widely in the media as COP26 has focused the general public's eye towards the issue. Whilst this is a simplification, it does provide a clear summary of what has been happening to the globe. Red means warmer than blue, and, as you can see, barely 2 decades into this century, we already see the dramatic impact of global warming. Rising temperatures are central to many of the impacts that we see around the world today, things like habitat loss and species migration, sea level rises, coral reef bleaching, and extreme weather events can be clearly linked to the planet getting warmer. Climate Action Tracker independently analysed government climate actions and commitments and used this to determine the likely temperature increase by the end of the century. With their finger on the pulse for the climate, they are able to provide predictions for the key milestones that need to be reached in order to achieve the goals of the Paris Agreement. Buildings last a long time, and as the UK Green Building Council have stated, 80% of the buildings that will be in use in 2050 have already been built. So it is paramount that from now on, all new buildings must be equipped to be net zero by 2050, and renovation rates must increase for existing building stock. This is especially important when we consider embodied carbon and whole life carbon. The guidance for how we can enable net zero buildings should be familiar. Drive down the need to consume energy in the first place, ensure that energy that we do consume is generated renewably, and utilise this energy in the most efficient ways possible via technologies such as heat pumps. The more we can reduce the emissions generated by the built environment, the less the burden of offsetting these emissions to reach net zero. As it currently stands, the technology does not exist at the scale needed to offset current level of emissions, so there is a lot of work ahead to get to where we need to be. Within the Committee on Climate Change's 6th carbon budget and accompanying report to Parliament, a stretch to a 75% reduction by 2035 was included and subsequently adopted by government. Many bodies are looking at this challenge. REBA characterised this in the twin challenges of operational energy, the energy a system needs to consume through its useful life, and the embodied carbon of the systems installed, the total impact of carbon in terms of the items that go into making a building. All materials, transport, installation, and ultimately handling at the end of life, where many of its materials can be recovered to make other items. It also calls for things to be done in the right order, yet another version of an energy hierarchy, in this case looking to drive down operational energy by at least 75% and between 50 and 70% of embodied impacts before offsets are considered. The UK Green Building Council has worked on a framework definition of net zero buildings, looking at the construction and operational phases as shown in the extracts here. Arup, the global design consultancy, has also looked at the route to net zero as shown on the right. You can see their current view on the left of a roughly equal split of operational and embodied carbon. However, over time, the required savings, or changes if you will, that are required are shown, along with passive measures, active measures, control and renewable technologies to make the biggest early gains. And as the grid improves and electrically driven solutions are selected, then another significant reduction can be seen by questioning what we build now and where we build, as well as driving waste out of the process. All of this before offsets need to be considered. So embodied carbon is starting to become an important consideration for buildings in all their forms. But a building is only the sum of its parts, so we need to account for the embodied carbon of the materials and equipment selected for the building, all the manufacturing of those materials, transport energy used to get them into the building, the energy consumed throughout the building's life, and ultimately the energy consumed at the end of the building's life. This is why the industry is looking for more and more data to be provided by manufacturers and suppliers such as ourselves. As the electricity grid becomes cleaner with more renewable energy generation, technologies that run on electricity will become more prevalent as their operational carbon emissions will be reducing. So as time ticks towards the net zero targets, the proportion of operational carbon and embodied carbon will start to shift towards embodied carbon. So how is embodied carbon calculated, measured and reported? Some of you may have come across the term EPD, which has actually been around since 2013, when the European standard EN 15804 was first released. But we are starting to see EPDs being requested more and more, and I've personally seen lots of specifications asking for them to be provided as a specific requirement. Currently not a mandatory requirement, and from the research we've done, there are very few EPDs in existence for HVAC products. So what is it? It's very much like the nutritional information on food packaging, but instead of advising you on the product's potential impacts on your waistline, it advises you on the environmental impacts of construction, operation, and disposal of the product may have. Until recently, they were predominantly aimed at building materials such as concrete, steel, and plastics, to help designers select materials that had a lower environmental impact when constructing buildings. But now the focus is widening to include the products actually used within the building. The challenge for HVAC products is that each product or family of products would need its own EPD certificate. And as I'll show you in the next couple of slides, there's an awful lot of detailed information required to reach a level to achieve an EPD certificate. Due to the complexity of mechanical, electrical and plumbing products, or MEP products, and their manufacturing process, there are options on how you can calculate and report the carbon emissions through the various stages of a product's life cycle. These are known as cradle to gate with options, and cradle to grave. The main point is that this is a difficult calculation, and most important thing for manufacturers such as ourselves is that we transparently share this information when we can with our customers. There is no right answer here. We just need to start to understand where we are today, report what we can, and identify areas where more data is required to help us remove carbon emissions from every aspect of the process. The calculation itself is known as the lifecycle assessment, with the outcomes of the calculation being the whole life carbon emissions of a product, which is shown as a kilograms of carbon or kilograms of CO2 equivalent. EPD are currently the most accurate method the industry has to report embodied carbon, but we all know how long it can take for a project to work its way through the various REBA stages of design, which is often years. But really, our house is on fire now, and we simply can't wait for all those detailed calculations to be carried out and certificates to be issued. So thankfully, in the meantime, SIBSI have provided us with a stopgap, TM65, or Technical Memorandum 65. They've worked closely with manufacturers such as ourselves to come up with a more simplified method of calculating embodied carbon emissions today, to help inform building designers and at least begin to impact projects on the table now, rather than waiting however long it will take to get to the point when EPDs can be provided for much larger product ranges that are available within the HVAC industry. SIBSI have provided two methods for calculating embodied carbon. These are called basic and mid-level. In this slide, you can see the various different stages of calculation required for an EPD, from A1 to C4, and how SIBSI's TM65 calculation methods compare. As you can see, the basic calculation uses various scale-up factors to allow for carbon emissions without actually having to calculate them. Whereas with a full cradle-to-grave EPD, you have to provide all this data. You'll notice that both TM65 calculations ignore the operational carbon of a product. This is because we already do this on every project in the UK. You know this calculation as compliance to UK building regulations via SAP or SBEM, where operational carbon emissions are calculated. So by using existing calculations and adding in TM65 calculations together, you can achieve a whole life carbon picture for a product solution. These documents that are generated from this calculation, such as this one for our CAHV 45 kilowatt air source heat pump model, are now becoming more available within the market. For our products in particular, they're available on our library website by just searching TM65. To explain the information provided, let's spend a little bit of time looking at an example mentioned. So you've got in the top left-hand side here the total figure, which is in kilograms CO2 equivalent, and it's displayed for quick reference and simple use. For products containing refrigerant, we choose to split this out and show this, and I'll explain a bit more about this later. There is also additional product information, which essentially forms the basis of the calculation, such as the weight of the product, service life, and product complexity. On our document, the second page shows the breakdown of the calculation result and the assumptions made, including refrigerant leakage rates, which are set out within the TM65, repair material replacements, and the amount of product not recyclable and therefore going to landfill at the end of its life. As this is a simplified method with assumptions, buffer factors are used to provide a more accurate account of the actual situation. Typically, the more actual data that is available, the lower the embodied carbon figure becomes. Looking at our reference heat pump product that I spoke about earlier and breaking down the embodied carbon, you can clearly see in a typical HVAC product where the main contributors are. Here you can see in A1 materials and B1 use stage. These main contributors and the reasons for variation to the value are mainly focused around the weight of the product and the life of the product. Materials, as you'd expect in these complex mechanical and electrical products, are a large contributor, with products typically contain weights of metals and plastics to provide effective vapor compression, heat exchange, air movement, and control of the many components within. Use stage focuses mainly around refrigerant leakage during the product's life, where due to the relatively high GWP of the refrigerants used in this product, this has a high impact and has assumed leakage rate of 2% on a GWP or global warming potential of that refrigerant of 1,774. As these are so large, transport and manufacturing in comparison, whilst considered to be perhaps big contributors, at this moment in time are less significant. This will change as materials and the use stage reduce through improved product design and using less and lower GWP refrigerants. Important to remember, however, with HVAC, and just additionally layered onto that same data, is the operational carbon, which still far outweighs the embodied carbon for these type of products. So we must look at products and solutions whole life carbon to obtain the clearest picture. Focusing on the materials within a product, when you break down the three main sections of the calculation, refrigerant, raw materials, and transport and manufacturing, refrigerant is making up over 50% of the total, with the raw materials making up around a third of this particular product. It's also worth noting that materials each have varying embodied carbon per weight values. So what is used here can make a big difference to the overall value. Embodied carbon is clearly an important metric, but must be and will be considered as part of other metrics on solution selection within the built environment. For HVAC, aligning with current and future directives and standards such as F-gas and the Building Regulations Part L, lowering GWP and using less refrigerant and then maximising optimal operational efficiency are key to reducing the overall carbon impact. Other factors will influence, such as limiting refrigerant connections on site, which influence leakage rates, and using larger systems, which maximises the chassis size and weight compared to its capacity, and therefore embodied carbon. This latter point, however, may be beneficial for embodied carbon, but potentially is detrimental in terms of operational efficiency and therefore operational carbon. We can also consider how product material selection and manufacturing location affect the overall figure, ensuring to keep a close eye on maintaining quality, safety, and effectiveness of those products. Of course, there are almost always needs into considerations in terms of noise, weight, dimensions, and functions, effectiveness, application, and of course cost. To give you a live example of the positive effects that this work and metric is having on our future product development, let me show you this example of our potential future CHV product, which I was talking about earlier. Focusing on embodied carbon, the F-gas directive, and the customer demand for a more sustainable solution, the proposed refrigerant, which has a GWP of less than 150 and less volume of it, reduces the overall embodied carbon by 50% compared to the current model. Further tweaks and feedback to the materials and chassis of the product have enabled a further reduction by 8%. What's interesting to see at this point is once the GWP of the refrigerant reduces to levels of around 150, its percentage of the overall figure is much less. So now the product itself, its materials, and its operational carbon are really where good ground can be made up. This can be clearly seen when we look at the whole life carbon, where this proposed improvement offers a 12% decrease in whole life carbon, with an equivalent efficiency to the current model. As we look to reduce the impact of future products, we then look to further technology innovation or work with customers on what compromises are to be accepted, whether that be in the building or the product. In the building, making fabric improvements to reduce loads, for example, or with product increasing its physical size, weight, and cost for improved efficiency, whilst minimizing the impacts to the embodied carbon. As we continue to receive data from our supply chain and more for individual products, we're able to produce more information into the market. In the meantime, though, we can use one of the other embodied carbon reporting methodologies which is being used in Europe, specifically France, called a Product Environmental Passport, or a PEP. This data reporting allows us as a manufacturer to scale up or scale down raw data for similar products within the same product range or family, rather than having to calculate each individual product. This should really help the industry to scale up quicker in providing the data and transparency that is much needed. And to conclude, products are obviously not used solely in a building. Components are often brought together to provide a solution to provide heating, cooling, ventilation. When it comes to direct expansion products such as split systems or VRF systems, there is usually additional refrigerant added on-site to allow for extended pipework separation. However, the embodied carbon of this additional refrigerant is not currently considered within TM65. And bearing in mind that we've just demonstrated that refrigerant can have a big contribution to the embodied carbon figure, I thought it'd be useful to just try and share a real-life example of this. In reality, we'd also have to consider the embodied carbon of the pipework and the ancillaries, but for now, this is an estimation of the plant and refrigerant to provide designers with some real system embodied carbon figures rather than just unit embodied carbon figures. So let's have a quick look at an R410A VRF system. In the small blue pie on the left is showing outdoor unit embodied carbon in the light blue and the factory refrigerant charge in the dark blue. Moving across, you'll see the additional refrigerant charge, which is based upon a long pipe run. So this is quite a worst case example. The purple pie is to represent the embodied carbon of the branch controller, one of the components, and the grey pie representing the 4 5 kilowatt indoor units delivering the heating and cooling attached to a 20 kilowatt VRF outdoor unit. As you can see, the large additional refrigerant charge and R410A, which is with its relatively high GWP refrigerant of 2088, is contributing around 2/3 of the total embodied carbon of this example total VRF system. So refrigerant really is the largest contributor. Our second total embodied carbon example shows Mitsubishi Electric's unique hybrid VRF system, which has significantly lower additional refrigerant charge due to water pipework being used instead of refrigerant between the branch controller box and the indoor units. This system also benefits from using a much lower GWP refrigerant, R32. What you'll also see is the total embodied carbon of a complete system such as this, with the same assumed long pipework separations as the previous example, being at around a third of the embodied carbon. We think that this demonstrates that even though we're only just starting to consider embodied carbon within the Hvac products, thanks to the likes of TM65, we're already looking towards providing the solutions needed into the future. And using this method, and we've just provided a quick estimate here of the embodied carbon on these different models to try and show how they compare across a building, taking this embodied carbon figure into a square meter. And as you can see, we could be as low as around 50 kilograms per square meter using our R32 hybrid VRF system, or as high as around 250 kilograms per meter squared if you're using R14A VRF. So embodied carbon within the Hvac life cycle is a very significant contributor to whole life carbon in the built environment. Whilst operational carbon has the largest impact, and therefore theoretical and in-life efficiency continues to be top priority, in the short term, refrigerant choice has to be the single most simple change to enable big dents to be made in the carbon associated to Hvac products. Thank you.
Thank you, Mark. That was a brilliant presentation and very apt in terms of what's going on with COP26 at the moment. Please, if you have any questions, do submit them into the Q&A, and hopefully Mark will be able to answer them. Mark, in terms of the demand from clients at the moment for this kind of information, are you getting a significant demand, or is it being driven by yourselves?
No, it's. I think from this sort of calendar year, the start of this calendar year onwards, we've really seen an uptick in the requirements, and we're seeing that being driven from a couple of areas. One from the consultant base and through the work that the SIBC and some of the other industry bodies are doing in putting these methodologies in place. Some of it's driven through legislation, and for example, the London Plan is looking for this data to be provided. But probably the biggest driver is from companies' commitments towards their net zero targets. Some companies are committing to try and be net zero by 2025, 2030, 2035. And they're really now having to study very hard what their current operation or their building portfolio looks like. And in order to do this, they need the data and the transparency to then being able to make the change. So that's really where we're seeing the drive coming from.
Oh, brilliant. And sort of in terms of the calculation, it seems very complex, obviously, because you have to look at a lot of data throughout the various phases. Is that relatively of information relatively available to do that kind of calculation? I know you alluded to TM65, obviously, but I'd be interested to know how easy it is to get that kind of calculation produced.
Yeah, so the calculation methodology that's been put together is once you kind of get your head around it, it's pretty simple to use. I suppose the complexity is the supply chain in providing this data, whether or not they've got that to hand, which luckily a lot of the data we have had to hand, but we weren't used to as a supply chain providing this openly for all of our products. So that's kind of where it's taking time, and also making sure that data is validated, is understood between our various different supplying plants, and we're providing that data in the same sort of format. So it's been a slow start, but it's definitely, from our point of view, really seeing an acceleration. And our intentions is now that every sort of new product that we have coming out comes out with this data being available with it as well.
And in terms of the presentation, you showed quite clearly, actually, the development cycle that you're going through in terms of product improvements to improve the embodied carbon, the operational carbon, and the whole life carbon. Are you already seeing that actually your next iteration of product solutions are being developed with that in mind? That's the key driver.
Yeah, definitely. It's I think what it kind of does is, it, especially in our products, is it's giving another metric that just bolsters up all of the other drivers that there has been. So, I mean, it's quite clear the refrigerant issue there in terms of embodied carbon is a real big one. And F-gas has been trying to do its piece to push that globally and on a European level, and now obviously on a UK separate level. But it's maybe not had quite the sort of the impacts and teeth that we'd have hoped it would have. Having this metric now has really given that clarity that, like I showed, you use one type of system with one type of refrigerant and then another one, you can make massive changes. So we're using this metric with our factories, with the discussions that we're having, and in particular with the French market, who are also in a similar place that we are, to start really trying to drive product development in that right way, so that it's that extra consideration when we're looking at products. It's efficiency of the product, it's the embodied carbon, it's the safety, it's the performance, all these things. It's an additional measure to look at.
And you mentioned obviously about changing the refrigerant. Does that actually impact the embodied carbon? Because I noticed you also went through a lot of detail in terms of how systems integrate. So is there necessary changes? Sorry.
No, that's fine. Yeah. So I'll say from what we can see, on a lot of the typical systems that we're providing into the market that use refrigerant, changing it to using less of it and a lower GWP does make a big impact. There's assumptions within the calculations of an amount of refrigerant leakage through a product's life, which there's arguments as to what those figures should be, but we have to have a baseline of what that looks like. And obviously, in reality, the better we can improve the quality of installations, the checking of those systems to ensure that refrigerant isn't leaked and any leaks are maintained quickly, which is obviously what F-gas is trying to do through the Hvac lifecycle, the less impact that will actually have in reality. But even then, decommissioning at the end of life and the fact that it does have a global warming potential is having an impact. So, we're trying to look at solutions that have less refrigerant, but being able to provide that same function, or lower GWP of refrigerant, being able to operate that same function. It comes with its additional considerations. A lot of the low GWP refrigerants are flammable or mildly flammable. So there's some more application considerations there, but it's a must. If we're moving towards these net zero targets, we have to make these changes.
Definitely. And in terms of, you also alluded with the presentation that you obviously integrate with lots of different systems, or there could be many components within a system. Do you actively get engaged with other parties to work in terms of developing that whole life cost model, or is it something that you model on behalf of your clients?
Yeah, so again, throughout this sort of early engagement, we've been talking a lot with Mitsubishi and the consultants that are working with them, and through various of the sort of the customers that we work with to really try and understand how it integrates and how our products fit within that piece of the pie. And it's interesting to see, when you're comparing HVAC products with the building fabric or the steels or the concretes or the everything else within that, and how that proportion fits within. I think I've seen a study that talks around a domestic property using an air-to-water heat pump, and it's a relatively decent proportion of the embodied carbon within a property, the MEP services. From memory, I think it's around 10 to 15%. So it's a real consideration and really something we need to continue to look at and continue to, really importantly, provide transparency and data so people can really understand where they are now, so that they can start making changes.
That's brilliant, Mark. Unfortunately, we've sort of run out of time, but once again, I'd like to thank you for your presentation. It's an absolutely brilliant presentation, and it demonstrates within the industry sector we're making real progress in terms of improving the whole life carbon management within buildings and their operation. So once again, thank you, Mark. Brilliant presentation.